live for a bit. Was hoping to be back here a little earlier, but I got held up with some cluster maintenance stuff. Or at least one of the boxes is back online now, though this one is going to be off until I get an extra cable for it. So, I think what we're going to do now is we're going to do a little bit of stuff on TTT. We are going to probably look at vtrace. I'm going to have a meeting at some point here. I think those are the two main things I really want to get today is TTT and vtrace. Okay. While I'm just sitting down here, I gotta say that Florida, this time of year, you do not want to walk outside and open your mouth. You eat a whole mouthful of bugs. Time to get out of Florida soon. Just in time for the new puffer facility. Alright. TTT. So this one. So I'd like to know where this graphic came from. Let me find the graphic. This is how it was described. Was this on the website or something? That's a funny website. Joint first and joint second authors. All right, guys. Yeah, I don't see where this particular graphic came from. Assuming that this thing is correct, though. Let me just read through it fresh now and see if I messed anything up. So, you initialize task, which is K, Q, and V. This does not get reset. K, Q, V, and extra yellow. Then on the forward, you make a learner, which we have init state here to give you model and optim, right? So you encode, and then state.train token. And then this is supposed to, I think this is just pseudocode, right? Because Brad is not a thing. So this is supposed to be task loss gradient with respect to the input, which is self.model. Do I have the stop grad in the correct spot? Gradient with respect to self.model. Believe so. Inner loop gradient. Let me make sure these match as well, because we have forward and forward train and they need to be the same. You know, I think I might have broken this thing. No, because the only thing that has a gradient here is the model output, right? I think that's the only thing that gets a gradient is the model output. And either way, the optimizer is only defined on the model parameters, right? So, Is it that the default learning rate is too high for the optimizer? Could be. Let me go check the original paper's code. Test. It's this thing, right? And they have PyTorch code, which is like massive. We do not recommend training with this code base. I mean, how are they going to write 1,400 lines and then say that this is the slow version? Okay, this is clearly not just a TTT layer, right? This is, yeah, TTT-LM. This is not just TTT. I don't know what the heck they're doing there. Last hidden states and gradients for TTT layer. Yeah, this is just insanity. Do I risk looking at the JAX code? Okay, I think this is the layer. Get QKV projections. This is not how it's described here. What the heck is this? TTT linear base? Surely this is simple. Somehow it's not. Yeah, this code base makes zero sense whatsoever. I have no idea why it's like that. And the thing is that the simple PyTorch is also not simple. The thing that annoys me here is I can't even like see how this is supposed to work because it's too much of a mess. Like this here, okay, so this is, they have weight and bias initialized. And then they do compute mini batch in here. XQ. Yeah, I don't know how this is supposed to be pre-computed either. This doesn't make sense. Oh, they're not using AutoGrad here. They're manually computing gradients. That's why. Okay, maybe I can get something out of it now. XQXVXK. Now the thing I don't understand is like why have they done this already? That's not how this thing works, right? QKV. QK. Oh, that is totally how this works. I'm dumb. That is totally how this works. Okay. So then I'm gonna have to check those gradients. Let me at least make this modification before I forget. Because you can do this, right? That can go there. That doesn't magically solve it. Right? So we look at, let me just make sure this isn't a learning rate thing. Doesn't seem like it. All right, let's see their code. I kind of see how they have it written this way now because this model breaks autograd, so they just didn't use autograd. Wait, what's trill do? Lower triangular. Why the heck do they have this? Inputs. Okay, let's read this whole thing. Batch, num heads, num mini batch size. I don't see time there. I do not see time. For pre-filling, we always use dual form. I have no idea what that is. I have no idea what dual they're, like, I don't know what they're doing with that. What is this? Layer norm? So we're not going to be able to read this because this is not going to match what they have otherwise. So this is the normal form. This is some weirdo trill. I also really can't tell if they have a time dimension. I think we ignore this because I think that this is because it's like multi-head data. This is not what's described here. The key here, though, is they compute the gradient with respect to W1 in the bias. They apply the step. Token ETA mini batch. So we should see what they use for this parameter, right? Token ETA mini batch. And then they store the last states. The last gradient, I don't know what they do with the last gradient. Also, when does this thing get initialized, this W1? They have init here. Are we going to be able to follow this? TTT linear. this is the only file. Do they have a train in here? Or is this just massive, crazy demo? TTT layer. Okay, what about the original paper? Okay, let's see. TTT layer. Oh, duh, he got it from here. Okay. What is this paper? This is a really wonky paper that was recently used in the NVIDIA 1-minute video generation with the Tom and Jerry clips. It is a replacement for an LSTM that trains the hidden state as part of the forward pass. It's very weird. I have it implemented and it doesn't do anything so far. Okay, let me actually start going through this live because I want to make sure I didn't miss anything. Our idea is to use self-supervised learning to compress the historic context x1 through xt into a hidden state st by making the context an unlabeled data set and the state a model. Concretely, the hidden state st is now equivalent to wt, the weights of a model f, which can be a linear model, a small neural net, or anything else. The output rule is simply call the model. Okay. Output token is just the prediction on x made by f with the updated weights wt. Update rule is a single step, one step of gradient descent on some self-supervised loss with learning rate eta. Why did that citation take me to here? Wait, it was supposed to be 2, right? They initialized the initial weights to 0. How does that do anything? Every heuristic needs to decide which input to remember or forget. RW remembers inputs that produce large gradients. One choice of L is reconstructing X itself. The forward pass of a TTT layer has a corresponding backwards pass. Our forward pass only consists of standard differentiable operators except the gradient operator. Calling backward on delta L means taking the gradient of gradients. Ah, shoot, so is this actually... I might have implemented this wrong then. TTT layers have the same inference as RNN layers and self-attention. Outer loop parameters are always denoted by theta. Hang on, an important difference between the two nested learning problems is that the inner loop gradient is taken with respect to W, the parameters of F, while the outer loop gradient is taken with respect to the parameters of the rest of the network. Okay. So where do they take gradient of gradient? Since both W and various thetas appear together in equation 4, we emphasize their difference in nature. In the inner loop, only W is optimized. Yes. In the outer loop, theta K, V, and Q are optimized alongside theta rest, and W is merely a hidden state, not a parameter. That's how I implemented it. The naive TTT layer developed so far is already efficient in the number of floating point operations. However, its update rule cannot be parallelized because WT depends on WT minus 1 in 2 places. Before the minus sign and inside gradient of L, yes. Since the gradient of L contains the bulk of the computation, we may focus on making this second part parallel. Wait. The general update rule can be expressed as this. The general update rule of GD can be expressed like that, where GT is the descent direction. Once we have calculated GT for 1 through T, we can then obtain all the WTS through a cum sum of the second half of equation 6. To parallelize GT for T is 1 through T, we can take all of them with respect to W0. What? That's completely different. To parallelize GT, we can take all of them with respect to W0. This variant is known as batch gradient descent. Since the sum is the same as the gradient with respect to W0 over x1 through T as a batch. That is an incredibly stupid analog. That is not remotely close to correct. Okay, I was wondering why I was getting weirdo messages about this paper that made absolutely no sense. It's because the paper makes absolutely no sense. No, when you're doing like batch versus mini batch gradient descent, you're going through different samples of the same data set that don't depend on each other. When you're doing a sequence modeling problem in which the state directly depends on the previous state, it's not batch versus mini batch gradient descent if you do it all at once or not. It's a completely different algorithm. Okay. God. For a proposed solution, mini batch gradient descent is shown in figure 6. Denote the TTT batch size by B. Oh. Okay, that's not mini batch gradient descent. That's not how that works. Whatever. What is this sum? Oh, this is the entire gradient update. Sure, whatever. Hang on, let me make sure I didn't miss anything. There are two potential channels to propagate information from WS to WT, where S is less than T. Cum sum and the gradient operator. The cum sum is always active, but the gradient channel is only active when WS is from a previous mini batch. Okay. It's a really weirdo approximation. Fine. Yeah, Ryan, it's a stupid. They're describing it really stupidly. They're drawing an analogy to they made some wacko approximation to like batch state updates over segments of time, and they drew some like wacko analogy to mini batch SGD that doesn't make any bloody sense. That's all. There's nothing to understand. It's just stupid. Like the technique is kind of okay-ish. Um, the description is just stupid. That's all it is. What the hell is this? I've been reviewing ML math for interviews, and I can never tell if I'm a moron or if the math in these papers is random. No, the math in these papers is usually pretty shit on average. Like, they clearly just hacked a thing and then, like, post-hoc came up with a bunch of math to justify it. But if you actually, like, read it bit by bit, it's just, like, it clearly doesn't make any bloody sense. Well, the thing is, like, I'm going through enough of these lately that I'm actually, like, getting that. So I'm getting better and better quickly at evaluating, like, which of these is likely to be bullshit or not. So before, I was going mostly off of experiments, right? But now I'm also looking at papers from the math, and I'm seeing whether I think that it's likely that the technique would be good when applied exhaustively to a bunch of environments or not as well. Also, the code for this is horrendous. Oh, this is what I'm doing on my stream. I streamed 10 hours and 40 minutes of this on Saturday. We implemented a CUDA kernel for vtrace. Fuck is this? Oh, this is just writing out the gradient. Okay, whatever. We cannot compute all B of the GTS through a single matmul. We need B outer products and compute them one by one. Oh, okay, fine. Yeah, there's this dual form. Okay, whatever. Is there an official definition of a dual form? Is this even the correct use of this term? Primal dual form. Yeah, I thought this was more precise. Okay, so this is not a dual. Okay, this is not actually a dual form. They're just like ad hoc using it because it's like, I don't know, we made a dual to the problem. This is like peak academic horseshit. Number has nothing to do with the number of dimensions. This is literally just saying, look, there's an alternative form of the problem, so we're going to call it a dual. That's not what a dual is. I'm not even a math guy, and that's not what a dual is, okay? So I see what they did. This is not even a dual. Like this is not a. This is not even the same problem, by the way. This is a efficiency hack for an approximation of the problem, and a pretty severe one at that. Look, this thing decays. Like, yeah, this thing decays like that. Let me get the implementation details to see if there's anything I missed, because this thing just doesn't work at all right now. Right? Yeah. 3 on breakout. Oh, wait. Learnable WO. The initialization WO is shared between all sequences, even though subsequent weights are different for each input sequence. Oh. Hey, welcome, Boxing Bites. Subsequent weights are different for each input sequence. I think I screwed that up royally, didn't I? Instead of setting WO equals 0, we can learn it as part of the outer loop. Since outer loop parameters are always denoted by thetas instead of w's, we assign alias theta init equal w0. Significantly improves training stability. Learnable learning rate. Base learning rate is set to 1 for TTT linear. Okay. How does this thing work with initial weight 0? So this is why they don't use AutoGrad for this thing. So we're not allowed to use AutoGrad. What's B's in it? They have a bias, don't they? They do have a bias, right? Maybe they don't have a bias? I could have sworn I saw one in there. Maybe they describe it as like an efficiency optimization or like a something. They don't. The code has a bias, right? Or am I dumb? No, look, grad B1 right there. You see right here, this is their initialization. We can use this. In TTMLP. Now, not TTMLP. We're doing TT linear right now. TTT linear. Why did they make this a parameter if they're not using an optimizer directly? A bit confusing why they do that. We do this. Head dim. Presumably this is per example or something. Oh, I see. Because this gets like broadcast expanded or some weird thing. That's fine. So this is just self.input size, self.hidden size. This is size. You don't need an optimizer, I guess. Are they learning X? They're learning this weight matrix gets learned per example, per trajectory. So you start with this, and then these params are learned as the state. So the state that usually comes out of the neural net, like out of an LSTM, they've made the state a network. It's weird. Very, very weird. Can I not use, wait, if I do make this a parameter, I can use autograd, right? If I can use autograd, it's not terrible. Is it an n-dot parameter? Yeah, it's an n-dot. mean, if I have to do it without, I'll do it without. But I'd like to at least not have the chance of screwing up the autograd initially. Because it is learnable, right? We want this to be learned. So I can actually just do this. This is W0, right? It's even easier. And now output equals that's not right either, though. How do they say that you should learn W? Learning MLP, it is self-supervised, yes. These are learned in the outer loop, they say. Wait. So this only gets learned in the outer loop. Okay. So I think then what you do is it's never the simple paper. It's never go implement the simple paper. It's always got to be the most complicated possible fucking thing. I guess I did get to do prioritized replay the other day, and that was pretty easy, huh? State.train. Pretty much every single descriptive piece of this paper sucks. Like, the method's actually pretty novel and interesting, but the description of the method, including the pseudocode, the code, the text, the map, every single part of it just sucks. So you give it, let's say we're going to get W in the state, right? So we're going to get W equals state dot W, TTT W, and then we're going to get B, state dot TTT B, right? Can't model anymore. And then this is going to be at hidden at W plus B, like this. Just add something here so I can actually freaking see. I think I can do this. Yeah, there we go. Okay, I just needed the at signs to be highlighted so I can freaking tell them apart. I never use these. I guess I could just torch map all it, but whatever. Okay, so now the loss we can still use this on, right? So this is model output. We'll call this TTT output. And this gets a label view. And then you kind of do want an optimizer with this, don't you? Pretty good. I think we can leave turn. Okay. We're going to take these variables. These have to be detached. It's very tricky because you have to be tracking which variables get detached and not. They do learning rate 1. Something like this. Okay, so now you have your output. Optim is state optim. You zero the gradient, you backward through this. Almost forgot dot detach. Wait, is it dot detach? This is so It's so sketchy. I think it's technically like dot detach dot expand. I'm gonna just do dot clone. For now. The thing that's really difficult about this whole thing, right, is this is pushing what AutoGrad was designed for, and you have to be really, really careful about like what is going to be taken a derivative of versus not. Otherwise, you break the whole thing silently. Okay, so hidden at W plus B. This should be the only operation that has a gradient, because in forward, all this is going to get called inside a torch no grad. So this enables gradient just for this off. You optimize this, and you should be okay. And then output is just going to be hidden at W plus B, like this. You decode the output and you're good. Okay. Let's bring this code down to the train pass and see if it's hopefully not terrible here either. Okay, so first of all, this state stuff. This goes up here, right? I guess there's no reason to have to. We can do this. Probably cleaner to do this. We still don't need, we don't need this until we actually do this loop, right? So now this has to be here, hidden at W plus B. This is TTT output. Step this gradient, or step this model. And then now this is where I think the thing that we just did is paid off. Hidden at plus B. I'm pretty sure that just works. And then you append this. And that's it. And then you do your GELU. We could just do GELU here just so we don't screw it up. Probably slightly slower, but it's probably worth it to not break it. Okay, so now all we have to do is figure out this new initial state shenanigans. Because it's W be an optim. State. Oh yeah, it's totally fine there. And I think actually this might be okay. Initial state. Missing batch size. Okay, that's fine. I did forget that. Do I know? Do I know the batch size? WordPass batch size? Oh, I see how we can even parallelize this nicely. Okay. I see how we're going to be able to do this as well. Data.totalAgents. Like this. And then in the backwards paths, it's going to be n samples. Cannot optimize a non-leaf tensor. Lovely. Where did we get this? In 224? Let's seriously break autograd. I mean, we don't technically need it, right? What's the gradient of this? It's like, it's something super basic, right? It's like the weight matrix, or no, the input, I think. See how they do this? Yeah, it should just be like the input, right? And you just absorb the 2. Yeah, gradient with respect to weight should just be hidden. Oh yeah, you do multiply by the difference, right? It's the loss. Can you seriously not just auto-grab this thing? Like, even if I do it here, it's going to make it such a pain in the ass to try the other version of it, right? Because, like, if I want to swap this into an MLP, I'm, like, writing my own freaking autograd again. Like, what do I need Torch for if I'm writing my own autograd, right? It's like, I've done it before. It's not fun. Let's see. Let me see if there's, like, a way around this. That's perfect timing. Okay, so this is just not picking up that there's been any optimization whatsoever. Let me see. Hidden at W plus B. Does this fail on the first pass? Or does it fail when making? Diagonalized. Is it because of the .clone or whatever? And optimize a non-leaf tensor. I can probably just do this. Maybe clone keeps grad information. Yeah, there you go. Element 0. How do I detach it? How do I keep requires grad but detach the earlier computation? Can I just do this? It looks like I can, right? And then it becomes deeply unhappy with me. Okay, that's better. Now we just have some shape mismatch shenanigans, right? Yet that was not the intent. By that. Oh, we get to get rid of the stupid at symbol syntax, right? Size of tensor. Oh, this just needs to be unsqueezed. That looks good, right? Ay, 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 ay. And then this one is just going to be shape. Okay, so we apply that to the backwards, and hopefully we can kind of do something with this, right? Oh, okay, so we do hidden unsqueeze 2 here. Let's just This should just be hidden as 0, isn't it? Or of t, I mean. It's one step at a time. Now what? Hidden of t. What happened to hidden? It needs to be unsqueeze 3. Actually, I think we should just do it this way, right? Star. Does that work? Yeah. Yeah, alright, so W times hidden. Plus a bias. Oh, because you have it, you dummy. Something like this, I believe. Yeah. A lot of, honestly, like a lot of my first few years in ML was just getting really, really comfortable screwing around with tensors. That's all it is. And how do I do this? You got the yellow, didn't you? So, yeah, we're gonna have some issues here with this. Lost out backward. Where'd my Optim step go? Be there. Okay, so that actually works. And then I'm assuming that it fails the second time. Yep. So, do W equals W. I think that's it, to be honest. I'm not sure, though. Really? State.optim. Oh, because this is going to copy. I think that if you do it with the underscore, it'll work. It'll do it in place. No? Can't have nice things today? Okay, torch. Okay. I see how it is. So why you do this? I figured that this would TTTW, and they only get modified by the optimizer, right? So when you do this, like this should be the first gradient creating operation, right? Heck, it actually shouldn't even be a problem. Oh, also, what the heck are you doing with your bias here? The bias should not be index labeled T like that. Hang on. Yeah, the bias should not be indexed with T. One 128, 128, 1. Yeah, so I don't know what the heck happened there. But this does not get indexed with T. It's only the hidden that gets indexed with T. Okay, so the first one is fine. Oh, you know what it probably is? It's probably this computation here, right? I don't define any loss over this thing, though, do I? Hang on, how does this work? Because I don't define a loss over this, so it shouldn't have a gradient, right? Or does torch not work that way? It should work that way, right? Let's just see. Okay, so that doesn't help. Okay, so this is already, with just this, it's saying that I'm doing a double. Prop, step, compute, loss, second backward fails. This variable gets redefined. So this only depends on W. Hidden. B. This is detached. And it's got to be trying to backprop through multiple steps of this for some reason, right? I would have thought that just detaching it. Maybe it is copying. Return tensor shares the same storage with the original one. So that probably is just not getting set in the optimizer one, right? But the detach underscore should have done it. Maybe you're not supposed to use that. This is just an annoying PyTorch quirk. detaches in place. It should be. Detach the source tensor. I would think that this is correct, to be honest. Like this seems like that should work to detach the graph, but it doesn't. Is there anything else this could be? Oh, I'm probably back propagating through hidden here, right? Yeah, I'm probably back propagating through hidden. Yeah, that's not me. Attached, hidden. This is what I mean when I say you have to be so careful with this method. Yep. So now it doesn't break anymore. We'll see if when I do this it breaks. Because now what you do is, do you want this one you detach here, right? Now it's W dot detach. This is like ridiculously carefully. Like this is like the autograd's honestly hurting you here. I see why they just did it without autograd. The autograd just hurts you. But the problem is, like, if you do it without the autograd, like, the MLP implementation is just gonna suck. Single linear is kind of fine. But yeah, the problem of not using autograd is that you don't have autograd. Where's the shape mismatch? Encoder. That seems a weird place to fail. Wait, why is that here? That should not be there. It's just an error. One of the variables has been modified by an in-place operation. Lovely. Do you need this, these W detachers or not? You might not need these. Okay. Then this should be on the main train backwards, right? Yeah, lost backwards. So this is new hidden. Stack. This is the right shape, isn't it? looks fine. Yeah. So, and maybe I'm doing this part wrong. Here you use the detached hidden and the trainable forms of W. And here you use the hidden and then the detached forms of W and B, right? And you append GELU of this. I don't know, freaking. Maybe we'll just do the anomaly, whatever. Does that give us anything? So it is this line. Yeah, here, bot. Does it expect both of these things to be differentiable or something? Okay, we're going to try. I'm pretty sure the original is the correct operation, but we are going to try this for the hell of it. It's not going to work, I don't think. I mean, we can try this, though. I guess it's the W's that it's, like, annoyed. Shit, the W's are being modified, right? Yeah, the W's are being modified. Yeah. Now this is going to be, like, giga slow, right? Oh, yeah. Take anomaly detection off, see if that does anything. Oh, yeah, okay. This learns a little bit. Let's just track it. May as well put it on Neptune. We got it to run. Okay. We can go put this to 80 mil as well. I added a 0. Okay. Put that to 80 mil. I'm gonna use the restroom real quick. I'll be right back. We're gonna run some experiments on this, and then maybe we'll do V-trace. Maybe we'll do some other stuff. I'll be back. Whoops. Camera broke. So, that doesn't look amazing. I think I'm gonna go chat with this guy about this method real quick, and then I'll be back shortly, and then we'll work on vtrace. So let me do that. Okay. So for folks watching, there'll be more back pretty soon. All my stuff is here. This will be open sourced if it's useful as well. So if you want to support my work for free, puffer.ai, start the GitHub. We're trying to get to 2K. Other than that, you can get involved with dev or just chat with the community on the Discord here. And you can follow me on X for more RL content. Thanks.